Alright, so today we're going to be looking at a problem in which we're going to try to use a Riemann sum with 8 rectangles to overestimate the value of some integral. Now the integral in question that we're going to look at today is the integral from -4 to +4 of f of x with respect to x, where f is given by this piecewise function that you see on your screen. Now, this is a piecewise function, so it kind of looks like a sawtooth pattern. Remember, it's a continuous function, so we can use these Riemann rectangles to approximate this. And the goal to keep in mind here is that we want to overestimate it. So that's going to determine how we draw the rectangles onto our function in order to determine how we're going to estimate this value of the integral. As you can see, I've already written out a few steps here on the screen. The first step of finding the delta x value, or the base of your rectangles, I already wrote up there. This should be a familiar formula for you by now. You want to take the right endpoint minus the left endpoint over the number of rectangles, which is why you see here you have 4 minus -4, the left endpoint minus the right endpoint, all over 8, the number of rectangles, which gets you a delta x value of 1. So I'm going to go ahead and just put dots on here in red where the base of each of our rectangles is going to be. And as you can see, it's just every one step. So now we're going to go ahead and start to draw the rectangles. And what we have to keep in mind here is that we're trying to overestimate the value of this integral. And so whether our function is above the x-axis or below the x-axis is going to determine how we draw these rectangles. Okay, so we're going to start on the positive side of the x-axis here, where the function is above the x-axis, where it's positive the entire time. And what we want here is we want our rectangles to be above the curve. Put another way, we want these rectangles to be the largest possible rectangles we can draw using either right or left endpoints. And the reason for that is that on this positive side, you can think about this area beneath the curve and in between the curve and the x-axis as being some positive area. So if we want to overestimate the value of this integral, we want the largest possible positive areas for these rectangles that we can get. So if we look at the first rectangle, whose base is going to go between 0 and 1 on the x-axis, we have to determine, are we going to use a left endpoint or a right endpoint here? And you can see pretty quickly that using a right endpoint is going to get you a larger rectangle. And so since we're on this positive side, the function is above the x-axis, we want that larger rectangle. So right here, I'm going to go ahead and draw in the first rectangle. And notice that we use a right endpoint here because we want the largest possible rectangles over here. And again, exactly the same thing is true when we're between 1 and 2 with our rectangle with a base between 1 and 2. We want the largest possible rectangle, and you can see pretty quickly that using a right endpoint there is going to get us a larger rectangle than if we used a left endpoint. I'm going to go ahead and draw in these last two rectangles where you notice we're going to switch to using left-hand endpoints because, again, that gets us the largest possible rectangles as opposed to using right-hand endpoints. So you notice two things about these rectangles on the positive side of the x-axis here. They're always above the function, and they're the largest possible rectangles we can draw by using either left or right endpoints. Okay? Now we had to switch between left and right, but that's okay. Because we're trying to overestimate, we can switch all we want. We just want the largest possible rectangles. So now let's move over to the left-hand side of this function, or the portion on the negative side of the x-axis. You'll notice right away that we're dealing with the function over here being beneath the x-axis. And so we're going to kind of have to shift how we think about drawing the rectangles on this side. And we have to think about how this area gets counted when we're on the negative side of the x-axis here and have the function below the x-axis. This area is going to get counted as negative area. Right? So we're going to subtract it off of this positive area for the rectangles that we just drew over here on the right-hand side. Okay? And so we have to think about, do we want bigger rectangles over here or smaller rectangles? And the answer is that we want smaller rectangles. Because this area is treated as negative and because we want the largest possible or an overestimation of this integral, we're going to want to shoot for drawing smaller rectangles here on the negative side of the x-axis. Okay? So if we look at this first one, if we look at the rectangle whose base is going to be between -4 and -3, when we think about using either right or left endpoints, you can see we're going to want to use a left-hand endpoint. Because if we do that, we have a much smaller negative area for our rectangle. If we used a right-hand endpoint, we would have a rectangle of area you can think about as -1. But since we're trying to overestimate the value of this integral, that is not what we want. Okay, if we look at the next rectangle here, whose base is between -3 and -2, you can think about using a right or left endpoint again, and you can notice that using a left endpoint is going to give us the smaller rectangle over here, which again is what we want. And then notice when the function starts to increase again, we're going to switch over to a right-hand endpoint there, because again it gets us a smaller rectangle on this side. And then again, this rectangle here between -1 and 0, we want the smallest possible rectangle there, so we choose a right-hand endpoint. So a couple things to notice about this section of the graph. Notice again that these rectangles are always above the curve, again, which is what we want. Anytime we overestimate, we always want our rectangles to be above the curve. And also notice these are the smallest possible rectangles we can draw on the negative side of the graph, as compared to the larger ones we drew on the positive side of the graph. Okay, so now that we have our rectangles drawn, we want to go ahead and estimate the value of this integral. You can see I've already written out the few steps over here, where we have delta x and then f of something. And we have to determine what those somethings are. Those somethings are the heights of the rectangles. But the nice thing is, when we write it like this, it's just f of something in parentheses, we can just use these function values that we have as the heights of each of the rectangles. Okay, so if we look at the leftmost rectangle here, we can see that it takes a function value at f of -4. Okay, and that's going to produce a rectangle of height 0. But for now, we just want to draw in each of these function values. So that's -4. The next step we have is the function value at -3. Oh, that's not a great 3. Let me go ahead and redraw that here. There we go. So f of -3. The next step, we use the function value at -1. So we skipped over -2 there in order to get these smaller rectangles on the negative side. We have f of 0. Next, you can just follow the function right over. It's f of 1. Then we use f of 2, another f of 2, and finally we use f at 3. Okay, and with these function values in place, now we can go ahead and just calculate this. We know our delta x value is 1. Then in parentheses, f of -4 is going to be 0. -3 and -1 each produce rectangles you can think about as of area as -1. Then we have another rectangle of area 0, a rectangle of area 1, 2 rectangles of area 2, and finally a rectangle of area 1. And if you add all this up, you find that you're going to have an over-approximation or an overestimate of this integral with a value of 4.